At that speed, a beam of light traveling from Earth takes more than 4 years to reach our nearest star neighbor. Crossing our galaxy takes 100,000. We are imprisoned in a cosmic jail, bound by physics' own bars. But what if the bars merely bent? Scientists have devised a mechanism for sending spacecraft 10 times faster than light, transforming century-long journeys into decade-long experiences. Warp bubbles appear in laboratories, gravitational waves conceal extraterrestrial tracks, and energy requirements fall from unattainable to just barely insane. If you're ready to see this breakthrough, click the like button and subscribe because we're going to rewrite reality. Let we begin. Our fastest spacecraft ever created. The Parker Solar Probe screams across space at 190,000 NOMPH. That sounds impressive, until you realize it will still take 70,000 to reach the closest star. That journey would begin during the last ice age and end in our distant future, where humanity is caught in a speed trap. We cannot escape using rockets alone. Light travels at 670 million miles per hour, and it takes 4.5 years to traverse the distance between us and Proximus. Center of the galaxy is 100,000 light-years wide. Complete the math and crossing. It becomes a trip that spans millennia. Every star you see flashing in the night sky represents a location that current technology makes absolutely unattainable within a human lifetime. The Voyager probes launched in 1977. We are now about 14 billion miles from home. They've been traveling for nearly 5 decades and haven't even departed our solar system's gravitational pull altogether. The stars remain unimaginably far. When it comes to sprinting, we crawl like cosmic children. Here's the terrible truth. Space is more than just big. It openly mocks our objectives. The distances between stars are huge. That even traveling at 99% of light speed would result in spectacular missions and generational commitments. Your great-great-grandchildren may witness the destination you longed for. Every propulsion system we've designed follows the same core premise. Throw something out the back to propel chemical rockets, fuel ion motors, electrified particles, nuclear engines, or heated gas. When compared to the cosmic highway, they all follow classical physics and move slowly. We need to cross. Scientists refer to this as the tyranny of the rocket equation. The more fuel you carry, the heavier your ship will get. The heavier your ship, the more fuel you'll need. It becomes a nightmare spiral in which your fuel tanks grow to be larger than entire towns. To achieve a fraction of light speed, increasing additional push just increases weight. We've launched robots to Mars, landed rovers on faraway moons, and photographed the limits of our observable universe. Yet we stay locked in our own backyard, staring at barriers we can't climb. The nearest potentially livable planet is 4 light-years away using present technology. Getting there would take 25,000 years of continuous flight. Something needs to change. The universe is full of billions of potentially habitable planets, but humans can barely reach the nearest rock in our own neighborhood. But what keeps us stuck in this painfully slow reality? The solution can be found in equations developed over a century ago by one individual. Albert Einstein published his theory of special relativity in 1905, and with it, he created an invisible prison for humanity. His computations showed something surprising. Nothing with mass will ever reach or exceed the speed of light. The universe imposes this norm through the fabric of space and time. The explanation is deceptively easy. As objects accelerate closer to light speed, they gain mass, and not just slightly. The faster you travel, the heavier you get as a spacecraft. Nearing light speed would weigh more than entire galaxies. Moving at even 1 mile per hour faster would necessitate enormous energy expenditures. This produces a cosmic catch-22. You require energy to accelerate mass. However, speeding causes that mass to rise, necessitating additional energy and hence increasing mass. The cycle continues into infinity. You are currently approaching the speed of light. The universe basically says, you can get near but never reach this limit. Einstein referred to it as a universal speed limit, and his calculations have stood the test of time for more than a century. Particle accelerators smash atoms together at 99.99% of the speed of light, confirming his predictions with terrifying accuracy. Objects actually do become heavier. Time truly does slow down. The rules are absolute. Scientists have tried everything to uncover loopholes. They experimented with unconventional propulsion technologies. They estimated trajectories with gravitational assistance. They proposed generation ships. Throughout the journey, entire civilizations would be born, lived, and died. None of this alters the core problem. Einstein's equations shut the door, and conventional physics cannot locate the key physicists. Breaking these laws, often known as envy, breaks causality itself. You create paradoxes in which effects precede causes, tearing away the logical structure that keeps reality together. The cosmos would rather collapse than have something with mass travel faster than light. Time dilation makes everything worse. Even if you manage to reach 99% of light speed, time will move differently for you than for everyone back home. A journey that feels like 10 years to you may last decades or centuries on Earth. You'd return to find everyone you knew dead, along with their great-grandchildren. The isolation is complete now that they are elderly. Length contraction adds another twisted layer at high speeds. Space appears to compress in front of you. Distances shorten a journey that should take years may feel like months to you. While decades pass outside, the universe warps around rapidly moving objects in ways that defy common sense across centuries. Physicists regarded it as the last word. Light speed is the speed limit. Nothing escapes it. Teaching this became crucial to every physics curriculum on the planet. Breaking it looked as hard as drawing a square circle or having 2 + 2 = 5. However, some scientists refused to accept permanent defeat. They started asking other questions. What if we're thinking about movement? All wrong, speeding even a little spaceship to light. Speed demands more energy than is currently available in each gasoline tank battery, and all of the world's power plants together. Then double this by 1 billion. You still fall short. The equations underlying this nightmare are confirmed and unequivocal. As velocity increases, so does kinetic energy near light. Speed. Energy requirements do not simply increase, they skyrocket. A spacecraft carrying only 1 ton would require roughly 9 × 10⁻XVI gems to reach light speed. That is equal to human civilization's total annual energy production consumed in seconds, simply to propel a small vehicle through nuclear fusion. The same procedure. Powering stars is our most energy-dense fuel source, yet even transforming the whole mass of a big asteroid into pure energy would only get a decent-sized starship to a meaningful fraction of light speed. We are not discussing complex engineering problems. We're talking about basic impossibilities. The Daedalus project, created in the 1970s, suggested employing fusion rockets to achieve 12% of light speed. It sounds modest until you see the design. A ship made entirely of skyscraper-sized fuel tanks that transports 50,000 tons of deuterium and helium. 3. The payload compartment for actual freight, and people would be small in contrast. Even with that gigantic ship, it would take 2 decades to reach the farthest limits of our neighboring star systems. Antimatter engines might hypothetically enhance this ratio. When matter and antimatter collide, they annihilate completely, transforming 100% of their mass into energy. It represents the most efficient fuel, Theoretically speaking, the difficulty. We can only create antimatter in one particle at a time. Massive accelerators and their storage necessitate the use of magnetic bottles, which use tremendous amounts of power. With current technology, producing enough antimatter to power a single interplanetary journey would take thousands of years. Some physicists hypothesize solar sails, which are enormous reflecting sheets propelled by light pressure from stars. These need no gasoline at all, just be patient. The acceleration is glacial, measured in fractions of an inch per second. Compounding over years, reaching even 10% of light speed would require decades of constant acceleration, and the sail would need to be miles wide, unimaginably thin, and strong enough not to tear apart. Every conventional propulsion technology strikes the same wall. The faster you wish to travel, the more fuel you require, and the more fuel you carry. The heavier your ship becomes, the more energy you will require to accelerate it. Engineers call this decreasing returns. Poets would describe it as cosmic mockery. Chemical rockets reach speeds of approximately 5 miles per second. Ion drives may reach 20 or 30. Nuclear thermal engines might theoretically reach 50. Even the most hopeful fusion concepts can reach roughly 3,000 miles per second. Still only 1% of light speed. We're throwing pebbles at a mountain, hoping to move it. The energy trap is about more than just larger engines and better fuel. It represents a basic barrier etched into the fabric of reality itself. Einstein's calculations guarantee that reaching light speed with any big object requires unlimited energy. Infinite means impossible. No clever engineering. There is no breakthrough technology. No amount of determination has changed that equation. The trap occurs only if you follow the old rules. What if mobility is not what we believe it is? Earth may be dying, and we have nowhere else to go. That chilly fact keeps academics awake at night because glancing around our cosmic neighborhood exposes a sobering reality. Every other planet in our solar system is a hostile environment, with Mars being the nearest candidate, a freezing desert with temperatures as low as -225 Fahrenheit. Its atmosphere is composed of 96% carbon dioxide and is so thin that standing on the surface is equivalent to being 19 miles above in Earth's atmosphere. Your blood would literally boil at the low pressure. Dust storms cover the entire planet for months, while radiation from space assaults the surface on a regular basis, since Mars lost its protective magnetic field billions of years ago. Venus appears even worse behind those heavy clouds. The surface temperature reaches 860 degrees Fahrenheit, which is hot enough to melt. Lead atmospheric pressure equals being 3,000 feet underwater on Earth. The atmosphere is largely composed of carbon dioxide combined with clouds of sulfuric acid. Probes sent Venus lasted fewer than 2 hours before being crushed and melting. Living there isn't difficult. It's impossible. The gas giants provide no surface to stand on at all. Jupiter, Saturn, Uranus, and Neptune are essentially massive hydrogen-helium balls. With crushing pressures and winds up to 1,000 miles per hour, their moons provide marginally better options, but they remain frozen, airless, and dangerous titans. Saturn's largest moon contains liquid methane lakes, and the thick atmosphere seems enticing until you consider the surface temperature is 290 degrees Fahrenheit. Without protection, you will freeze solid in seconds. Europa is orbiting Jupiter. It may contain liquid water beneath miles of ice, but getting to it would require digging through a frozen crust in one of the solar system's most radiation-rich regions. Mercury's temperature ranges from 800 degrees on the sunny side to -300 degrees in the shadow. The moon has no atmosphere or water and is subjected to the same radiation assault as Earth, but lacks a protective magnetic field. Every body in our solar system is either too hot, too cold, too toxic, or altogether devoid of the essential elements for human life. Terraforming these worlds is just guesswork. Even the most optimistic projections suggest that making Mars slightly habitable would take thousands of years and need technology that has yet to be devised. We would need to thicken its atmosphere, reheat the surface, and reactivate its magnetic field, and make breathable air. Each step poses seemingly overwhelming hurdles. Earth is more than just our home. Even with limitless technology, it may be our sole viable home for millions of years in the future. That is, if climate change, asteroid impacts, or any other calamity renders the world uninhabitable, humanity has no backup plan. We need to get beyond our solar system, not for exploration, but for survival. The dilemma is that possibly livable worlds are light years away. Proxima Centauri orbits in its star's habitable zone, just 4 light-years away. The TRAPPIST-1 system features 7 Earth-sized planets, 3 of which are potentially habitable 39 light-years away. Kepler 452b, Earth-like planet located 1,400 light-years away. These worlds symbolize our future houses, but given current technology, they could exist in another dimension. This is why faster-than-light travel is not considered a luxury. It's an evolutionary requirement. We need new worlds, and getting there requires overcoming the most fundamental speed constraint. In physics, telescopes have detected over 5,000 auto-confirmed planets orbiting distant stars, including several in the habitable zone, where liquid water may exist. We can see them, we can determine their dimensions, composition, and orbital distance. We can calculate the surface temperatures and atmospheric composition. We simply cannot contact them. Proxima Centauri worries astronomers because it represents all we want but cannot have, while being only 4.2 light-years away. This planet circles a red dwarf star within the habitable zone. It may have oceans and support life. Early data suggests it may even have a magnetic field to protect it from radiation, and scientists believe it receives similar energy levels from our star. The TRAPPIST-1 system, uncovered in 2017, fueled even more interest. 7 Earth-sized planets orbit a tiny cold star about 39 light-years away. 3 of those planets are firmly in the habitable zone. Computer models indicate that they could have atmospheres, weather systems, and stable climates. Kepler 452b indicates that liquid water is not only feasible, but also likely. Earth's cousin, orbits a star, is strikingly similar to our own. It receives only 10% more energy than Earth, indicating surface temperatures suitable for life. It is 1,400 light-years away, and discovering it felt like finding a twin sibling across an unbridgeable ocean. Every year, dozens of new contenders are discovered, including planets with thick atmospheres, worlds with day and night cycles comparable to Earth, and rocky planets with precisely the proper mass to retain their air without crushing anything on the surface. We discovered freezing worlds, lava worlds, ocean worlds, and desert worlds. The galaxy is full with possibilities, yet none of them are within reach. Even Proxima Centauri, our closest possibility, takes 40,000 years to approach at present spacecraft speeds. TRAPPIST-1 would require 600,000 zeros. Kepler 452b requires 25 million years of continuous flight. These numbers no longer represent journey times, but rather geological epochs. We're locked behind a window, seeing heaven. We cannot enter. Astronomers can tell you the atmospheric makeup of planets dozens of light-years away, yet we couldn't even send a modest spacecraft to explore them in a realistic period. The James Webb Space Telescope can image the chemical traces of water vapor and oxygen in extraterrestrial atmospheres. However, physically visiting those places remains pure fiction. The frustration extends beyond scientific interest. These planets are potential homes for future generations. They could serve as refuges. If the Earth becomes uninhabitable, they might contain ecosystems we could study, we could use resources, or even contact intelligent civilizations to learn whatever we want to know. But everything we need to know is just beyond our reach, hidden behind an impassable wall of time and space. Radio signals. It would take years to travel at light speed between these worlds. Even if we identified intelligent life today and sent a message, the response would take decades. A discourse might span centuries. Physical travel appears unachievable without a thorough reimagining of how movement works, unless we stop attempting to move across space and begin moving space itself. Miguel Coor, a PhD student intrigued with Star Trek, sought to investigate whether warp drive could function in real physics. In 1994, he published a study that made professional physicists think twice, because his arithmetic was both imaginative and technically correct. The LQBI air drive concept does not propel a spacecraft across space at all. Instead, it forms a bubble around the ship, warping space itself. Space contracts in front of the vessel and expands behind it, creating a wave to propel the bubble ahead. The ship within remains immobile in relation to the space immediately around it, with no acceleration forces applied. Imagine a surfer riding a wave. The surfer does not swim through the water or generate their own speed. They are being transported by the wave itself, standing there on their board while the ocean does all of the work. Al-Kubi's calculations envisaged a spacecraft riding a wave through space-time in precisely the same way. The brilliance stems from exploiting a flaw in Einstein's calculations. According to relativity, nothing with mass can move faster through space than light. Okay, but Einstein never asserted that space itself cannot move faster than light. In fact, cosmologists understand that space expands faster than light toward the boundaries of the observable cosmos. That expansion is how the cosmos grew from a small point to its current size in just under 14 billion years. If space can already exceed the speed limit, why not use that ability? Our Cube-Res equations demonstrated that you might hypothetically create negative energy density in front of a ship, causing space to contract there. While positive energy generates expansion, the asymmetric space-time distortion propels the ship forward. The ship merely rides the wave, with no thrust or acceleration sensed. For the first time, his paper shook the foundations of theoretical physics. Someone described a mechanism for traveling faster than light using established general relativity equations. It wasn't speculative science fiction. It was peer-reviewed mathematics published in a reputable physics magazine. The procedure appeared to be technically legal based on established physical principles. Other scientists hurried to check his calculations. They discovered that the arithmetic underlying spacetime might conceivably be bent in this fashion without violating causality or breaking relativity. The energy requirements are truly gigantic, yet technically finite. This marked a significant advance over traditional propulsion, which required virtually unlimited energy to achieve light speed. The Al-QBI drive may theoretically achieve any speed, including 10 times light speed, 100 times, and 1,000 times. Since the bubble is not moving across space, relativistic phenomena such as time dilation and length contraction do not apply. Crew members inside would have typical time flow. They would not age more slowly than individuals back home. They would not observe distances compress. Physics inside the bubble would remain entirely normal. Al-Kubri acknowledged that he never expected the concept to function mathematically. He was just a physics student experimenting with mathematics, inspired by his favorite TV show. However, his recreational calculation unintentionally exposed a genuine possibility hidden in the nature of space-time itself. Reality looked to have a cheat code built into its operating system. Of course, actually building one created challenges that made the theory appear very trivial in comparison. But once the door was open, the impossible became incredibly tough. Space-time is not empty, nothingness. It is a real phenomenon. A cloth that can flex, stretch, twist, and ripple. Every large object, such as bowling balls on a stretch sheet, causes a depression in this fabric. That dent is what we perceive as gravity. Einstein described this over a century ago, and we have proved it numerous times. GPS satellites must account for time moving slightly quicker in orbit. Then they reach the Earth's surface because they are higher in the gravitational well. Experiments with atomic clocks on airplanes demonstrate the same phenomenon. Black holes twist space-time so badly that nothing can escape. Once you've crossed the event horizon, the Alcubierre drive weaponizes the notion. Instead of allowing gravity to naturally bend space, you intentionally build a bubble of twisted space around your spacecraft. The warp contracts space in front of you while expanding it behind you. Create a wave that propels the bubble forward. Your ship never travels in space. Space moves around the ship. It sounds like semantics until you grasp what's going on. Eliminates Einstein's speed limit altogether. Relativity slows movement through space, but does not limit how fast space may move. The distinction is important, because all of the terrible side effects of near light speed, travel time, dilation, length, contraction, and limitless energy requirements vanish when you are not moving during the stroll. Bubble physics runs normally. You can roam around the ship, sip coffee, and play cards, and time flows at the same rate as it does on Earth. There is no twin paradox, in which you return younger than your siblings. There is no relativistic effect that blurs your eyesight. The bubble separates you from the extreme space. Time distortions occur at its edges. The wave itself could travel at any pace. AKB's original calculations indicated 10 times. The speed of light would be quite straightforward. More subsequent iterations have proposed speeds that are 100 or 1,000 times quicker. At those speeds, Proximus and Centauri become a 2-week trip. The entire Milky Way galaxy becomes crossable. In a human lifetime, outside onlookers would find the warp bubble unusual. Light cannot ordinarily escape from the extremely compressed area in front of the ship, rendering it partially invisible. The growing space behind would cause light to shift to radio frequencies. The bubble may have emitted exotic radiation as it moved, leaving a visible wake through space-time itself. From the inside, you would perceive space compressed ahead of you, making faraway places appear closer than they are. Stars would change hue as their light was affected by the walk field. Looking backward, space appears to stretch into infinity, but you can still perceive your beginning point through shifted wavelengths. The mathematics describing this become increasingly sophisticated, incorporating tensor equations and differential geometry, but the essential concept remains stunningly simple. Surf space-time like an ocean wave, allowing the cosmos to do the job while you relax inside a bubble of regular reality. The trick is to create asymmetric space-time curvature, which entails changing space's energy density in seemingly mystical ways. This takes us to the most serious issue with the entire premise. AQB's warp drive requires something that most likely does not exist: exotic matter. With negative mass and energy density, this is not antimatter, which destroys conventional matter in bursts of energy. This is even stranger: it repels instead of attracts, pushes instead of pulls, and reverses gravity. Normal matter curves space-time inward, forming gravitational wells that keep planets in orbit and cause apples to fall from trees. Exotic matter would bend space-time outward, forming a gravitational slope that pushes objects away. It symbolizes the polar opposite of all we know about how mass and energy interact in our universe. Does negative mass exist? We have never witnessed it firsthand. Nobody has ever measured it, made it, or discovered proof that it occurs naturally anywhere in the universe. It remains totally theoretical, a mathematical possibility allowed by general relativity's equations that nature appears to have never manifested. The amount required for a warp drive makes matters worse. According to Alcubre's original estimates, warping space around a small spacecraft would require negative mass equivalent to Jupiter's total mass energy. Jupiter weighs 300 times as much as Earth. Converting that much normal matter into exotic matter, even if possible, would necessitate massive energy expenditures, dwarfing anything humans could produce. Critics seized on this requirement instantly. Yes, the math works. They stated that the calculations are correct, but requiring materials that do not exist renders the entire concept meaningless. You might as well create a perpetual motion machine powered by unicorn tears. The physics is correct, but the elements are fantasy. Some researchers attempted to identify alternatives. Could you utilize strong electromagnetic fields to produce negative energy density in a vacuum? Perhaps quantum fluctuations can be managed to get the desired result. Dark energy, the unknown factor that accelerates the universe's expansion, has several features akin to negative pressure. Could we harness or concentrate? These questions resulted in decades of theoretical research, but no practical answers. Creating long periods of negative energy density appears to break several fundamental rules.